So, we come to this class and take the story further on the false twist texturing. Part of characterization and optimization, part of characterization we have done, and this time we will try to complete some of the things which are left out. And how do we optimize? Optimize means that you got to have some parameters on which your properties depend, and so hopefully you will have some control on finding out how to change those and get to an optimum property. So, this is what we will try to see. May not be in this whole class, maybe we will have to go to the next class as well. So, what did we do? We had learnt that in the context of false twist texturing, setting, that is thermomechanical setting, is one of the most important steps, and there are some things which we must control, or if we can control, they would help to do better setting. And in thermomechanical setting, we understand we are looking at release of energy. Then also we looked into which parameters, and we did talk about a crimp rigidity test method. And why we are talking about evaluation is that when you talk about optimization, you know how to evaluate. First you should know, then only you will say, well, this is better or this not so good. So, let us look at the characterization itself. We did talk about this method called the Hatra method. So, this is called crimp rigidity. So, higher is the rigidity, better is the texturing, we may at least conclude. What it means is that it recovers much more after the load. So, if it recovers less, then obviously it is not so good. So, this is how we will work on. You remember the first fiber which somebody wanted to make synthetic fiber, actually people who wanted to make polyester, but they ended up making nylon, all right. So, therefore, the whatever happened on texturing also happened first on nylon and then on polyester. So, when it came to how to evaluate the crimp characteristics of a textured yarn, which was also nylon, so the initial method was designed for nylon. And what was the method? So, the test was conducted on lees. So, they made some lees of the textured yarn, all right. And now we will say we are supposed to load and unload, okay. So, we will be, you can have some way to hold it, the lee. So, this could be some stand, all right, on which you can hold the lee, and then you put some weight which you initially, you have a light weight which we called at the 0.00002 grams per denier. Then you also put a heavy load, so which was, let us say, 0.1 gram per denier, and this whole thing this experiment was conducted in water. Experiment was conducted in water. At room temperature, of course. Well, you can define the room temperature also as 25 degrees plus or minus 2 degrees in any setting, testing environment. But this whole thing was in a jar where this lee was hanged into the water, and then later after a certain time the heavy weight was removed, it was allowed to go and contract, and then measure L1, L2 and get to your whatever value of crimp rigidity. Okay. So, the question is, why did they do in water? Because doing any test in any liquid is clumsy, right? Why would somebody do that? And here is one concept which we wanted to talk to you earlier, we had probably discussed earlier, was called the temporary set. That means, when somebody opened a textured yarn package and took the yarn out, they almost saw there's hardly any crimp there. And so, what do you test? And if you actually test that and there is no recovery or not as much recovery, it will give you a bad result anyway. So, one fear was that maybe we have lost everything during this storage period, but when they found that you do any kind of a stress, thermal, mechanical, so it comes back. So, this new condition where almost everything appeared flat was only a temporary condition. Automatically it was not going up, contracting, but it needed help. And it was obviously, when you put anything of nylon in water, the glass transition of this polymer goes down, and so the molecular mobility also starts, and suddenly you find that all the crimps which were seemed to have been lost somewhere again come back. And so, this test was designed to be conducted in water, all right. But later on people found that there could be other methods also. You could actually make the lei, put it in a hot oven for some time, then it would also recover. So, this was the test which was designed initially. So, nylon we have understood. So, what about polyester? Will it be any different? So, two things people found, that by putting polyester yarn, textured yarn in water, it did not help, because polyester is too hydrophobic and its glass transition temperature does not get affected by water. So, if there was a temporary set, the temporary set remains. So, what do you do? So, either you raise the temperature of water, or as I said, you can put it in some hot oven at a temperature which is above the glass transition temperature, and glass transition temperature of the polyester will be 70 to 80 degrees. So, you try to get to that and suddenly you will find the crimp developed. So, instead of doing the test in the water, they said ki we will heat it up and then do the test, because why we heat the water, which will be more difficult process while the test is being performed, why not do it. So, you make separate leis, whatever number of tests that you want to do, put them in oven, they will obviously get contracted, then you bring them up, then test them in air at room temperature, without water, right. So, that is called modified hetera test. So, this is modified, because the original hetera was do it in room temperature at water. They also found that polyester, because of its aromatic rings in the molecular structure, is relatively more rigid compared to nylon, which has no aromatic ring, is basically an aliphatic structure, more flexible. And so, to remove all the crimps, you needed more stress. So, instead of 0.1 grams per denier, it was suggested that you can do 0.2 grams per denier. It is very low again, it is not a very high stress, but it is double the previous one. So, they realized, at least some of the researchers realized, that if you do 0.2 grams, use 0.2 grams per denier, then all the crimps are removed. So, the first length that you measure is when all the crimps are removed, and the second is just recovery, which was still kept at 0.002. So, that is why this was called a modified hetera test. All right. So, we are looking PET only because that is the most popular textile yarn that you have, although polyester as general, there are many polyesters which are also useful and very nice. So, that was about the crimp rigidity. The other test you may be interested in is the stability of whatever crimps that have been generated. Whatever texture has been made, how permanent it is. One test you do is gets a value, then you go to the next league, do another test, you get another value, average amount and get to the value. But let us say in a normal condition, let us say somebody who is wearing a textured yarn garment, and then he is sleeping in a certain posture, and the yarn from that area has been stressed for a long period. Okay. If it is stressed for a long period, then this is a condition which is more stressful than the condition of a test, which is stressed to only 1 minute and then recover. In this case, maybe depends on who is sleeping, 6 hours, 4 hours, 8 hours or more. Then you are expecting this to recover from that. Now, what happens is, if suppose your material for whatever reason creeps, okay. Creep is a test under stress, is not it? So, if this material creeps, then you will have a different situation altogether. Now, somebody may be interested, I not only want the initial test, I want to know how will it happen. So, that kind of a thing could be called a static type of a test, like stressed in an approximate static condition for a long period. Other the dynamic test you may like to conduct, where for example, athlete is jumping and you have a frequency at which it is stretched and recovered, stretching and recovering. So, you can do a dynamic test of stretch and recovery. You do some number of cycles and then see how good or how bad it is. Okay. So, you may be interested in something called a crimp stability, which also means a combination of the properties of the material that you are handling, texturizing, versus the stress levels that you give or the setting that you have done. So, how can we measure the static crimp stability test? We can, this is there. So, you do the crimp rigidity, without stress, then you put a stress, which means the 0.002 plus 1 gram per denier, let us say in the case of nylon, or 2 grams per denier. The stringent test could be you load it for 24 hours, which is really stringent at room temperature. And then you remove this, let it recover, maybe depends what kind of test you can design. maybe for 1 hour, let it recover. This is also too much of time, people will like it to recover within few minutes, but let us say. And then do crimp rigidity test again. So, you will find that if there is a loss in crimp rigidity. So, how much is the loss, percent loss? You can calculate. So, the percentage loss in crimp rigidity will give an idea that whether the setting was good or if the material that you chose to texturize responds differently to the stress levels, right. So, this test can be performed and you can say if the loss of this is less than 5%, should be quite happy that is not bad. But if it is more than 10%, you may start giving advice, do not do this, do not do that, like you get a care advice, do not wash in 80 degrees, wash at room temperature, etc., etc. So, or tell the guy that this is not good enough, we have to do something else, right. So, this is one of the ways in you can evaluate your material. The dynamic crimp stability test, what it means is that you will be doing some cycles of loading, unloading, right. So, one of the ways the people suggested is let us say on this side I am plotting stress. So, loading means there is a strain also, and from where to where you say, well, 0 is here, there are levels I am fitting 0, 0, 2 and let us say 0.1 grams per denier. Okay. So, these are the two levels where I may like to do the cyclic loading. Let us say you, for whatever, you get a curve, then you do unloading, then loading, then unloading, then loading, then unloading. And what do? We can measure the area under recovery curve . So, this is the thing and this is the recovery. So, you measure the area under the recovery curve in each cycle, right. So, you may start with the cycle 1 and let us say you have cycle 5, sometimes people may go to cycle 6. So, recovery, the energy, so you are measuring the area means the energy. Okay. So, this of course is extension. So, you get obviously some hysteresis every time you go up, whichever curve it follows, depends on what you are putting on. It follows a curve, when it comes back you find it is coming differently, that is the hysteresis, all right. So, if the change happens too much, then the hysteresis will be more. If the change is less, then hysteresis is less. 0 hysteresis will be the best, it may not happen. Because what happens is, this test can be performed let us say on an instron tensile tester, where the jaws keep moving up and down at a certain speed which you fix, so many centimeters per minute, all right. This is the way you will do the extension part of it. But limits are set by stress. The moment the stress becomes 0.1, start coming back. When it becomes 0.002, start going up. So, this cycle can continue. So, you are going up to the fully decrimped state to a recovered state, and that is the way you can test. So, the loss of energy, that is the under the recovery cycle, percentage loss of energy under the recovery cycle can be considered as the measure of crimp stability. If loss is too high, then obviously stability is low. If the loss is less, stability is high. Is this clear what I am saying? So, on an instant machine, you can load your textured yarn or a bundle of textured yarn, where they are loaded up to, let us say, 0.1 linear. So, fully loaded, then you allow them to recover up to 0.002. So, in this cycle you can do. This kind of cycle can be done where you can fix the extension levels, but because the crimp rigidity test says that we work in 2 stress levels. So, this is the stress level, you can fix it up. All right. Here also, if the difference between the 5th cycle and the 1st cycle loss is less than 5%, you can still be satisfied, or more than 10, you should be dissatisfied, and so there is a range you can work around. So, this is the dynamic crimp stability test. So, important crimp characteristics therefore are crimp rigidity and crimp stability. We mentioned the tensile characteristics such as tenacity at break and elongation at break, although are not so important, because generally during use your yarn is not going to be extended to that level. If it extends 300%, 400%, your stretch at any given point of time in a garment may be 30%, 50%. So, it is much below, but we still measure and we can report also. I have done this texturing, this has happened, that has happened, and which also could be important in some cases. Now, we go to the next part of this discussion, whether the parameters which will affect the texturing. Texturing means we are looking at crimp rigidity, we can look at crimp stability. So, we are talking about that, which in turn also means whether you have done good setting or a bad setting. So, it is not that independent of that. Setting, twisting, setting and detwisting is part of the whole process, but this type of a behavior that we call whether it is good, nicely set or not so nicely set, would be determined by the crimp characteristics. So, I am just repeating again that when we visualize whatever discussion that we are having, we are still in the under these conditions that fully drawn thermoplastic yarn, thermomechanical texturing, and it is twist texturing, no other texturing, and at the moment we are looking at single heater texturing machines. Okay. We are not even looking at double heater texturing machine. So, we are basically saying stretch yarns and not even modified stretch yarns. So, obviously, there are 2 types of parameters that you may like to discuss. One is the material related parameters, other is the process related parameters. So, material parameter, which type of a fiber that you are actually wanting to texturize, what are the dimensions of the material, how many number of fibers it has in the filaments, all those kind of things will be important, the material characteristics. And the process means we know it is a thermomechanical process. So, there is temperature is important, time is important, how much twist are you giving, that could be important, and also maybe how much stress that you want to put while you are texturizing, what is the stress level. You remember last time we said that if you have a stressed yarn, and this process of setting is a relaxation process where the molecules can take up certain positions. So, that can be restricted if you put stress. So, those will be the process parameters, and then we have the material parameters. So, in the material parameters, obviously we should be concerned about which type of fiber we are using. We should also be concerned about the morphological characteristic of the material. Does it crystallize? What kind of crystallinity does it have? Is it oriented structure? Not so much oriented structure. And crystal itself can have different structures. So, crystallinity is one part, but within the crystallinity you may have different type of crystals present. So, different materials obviously respond differently, and then other properties, characteristics that you may be interested, specific heat, thermal conductivity, modulus of the material, the denier, total denier, and filament denier, which is individual filament denier, right. So, total denier is a 300 denier material that you are texturing or 80 denier material you are texturing. Does it have 36 filaments or got 15 filaments? So, all that is part of a material. Some of it you may have control. Oh, I will not texturize 35 filament yarn, but your client says you have to. So, only thing you have to understand whether it will have some impact, and based on that you may change something, all right. So, polyester, polyamides, polypropylene, polyacrylonitrile, acetate, triacetate, which one of them is not a thermoplastic? Which one of them? So, most of the people are saying acetates are not thermoplastic, right? But that is wrong.
All are.
They are all thermoplastic, and theoretically all of them should respond to thermomechanical texturing, theoretically. So, obviously in this whole thing it is the chemistry of the fiber which should be responsible for how does it respond to any thermal input. And what do we want ultimately? Ultimately we said these molecules should be freed, they should be allowed to take up positions within the fiber in a crystalline region or in the amorphous region, whatever they want, and we cool them. Cooling is our thing, heating is that, but what happens within the molecule is spontaneous. You can't guide each and every molecule, do this, and therefore, the chemistry of the material is obviously important. Therefore, polyester behaves differently than polyamides and the polypropylene, other than the things which we call as optimum temperatures, which will be different for different polymers because they melt at different temperatures, they soften at different temperatures, the glass transition temperature are different. So, there the chemistry is playing a role. Okay. Among these things, as we now understand, all of them are thermoplastic, they should respond. The ones which people love are these two definitely, and here this also. And we are talking about textile grade material which is available, because when you heat these three, first of all you remember they are all melt spun material, and so they do very nicely respond to thermal input. What it means is that they would also crystallize very easily. Of course, the rate of crystallization each one of them is different. The fastest crystallizing will be polypropylene, then the polyamides, which is the nylon for example, and then polyester being a rigid ring. Polyester here is we are, let us say, we are not talking about all polyester, not all polyamides, we are talking about let us say or polyester, which is the polyethylene terephthalate. We are also talking about, let us say, nylon 6 and nylon 6,6, polypropylene. So, these are the commercially available material which are for the textile applications. All three are good. They are considered good texturizable material, because they do respond to heat and do change morphology, during this process. These two are not really considered very good material for texturizing. Which texturizing we are talking about? False twist texturizing. We are not talking about general texturizing, right? This part, the constraint, the boundary conditions of discussion. Polychlornitrile, which is otherwise a beautiful material, acetate, triacetate, they are thermoplastic because the hydroxyl groups have been replaced and the new group of the acetate does not form that type of hydrogen bonding. You see, otherwise the cellulose, the cotton, the viscose forms a lot of intermolecular hydrogen bonding, and therefore, when you heat it does not melt. Such intense is the hydrogen bonding that the main chain degrades before the intermolecular chain starts separated and can do whatever they feel like doing, right. So, these materials are not melt spun, they degrade. Okay. And because they degrade, then how can you do texturing? Right. So, they degrade. So, you do not want a degraded material and say, now I got a textured yarn, be happy about it. Acrylic fibers are very sensitive to heat. Something will happen, they become yellow very quickly. And similarly, acetate and triacetate are also thermoplastics, because the capability of formation of intermolecular hydrogen bonds is reduced drastically. In triacetate, all the hydroxyl groups have been taken care of. In the acetate, at least 2.2 to 2.7 out of 3 have been taken care of. So, they do not form hydrogen bonding. So, they would respond to heat. All right. So, you understand what I am saying, but still not considered good for texturing. And again I am reminding, the texturing we are talking about thermomechanical texturing. So, difficulty level, for example, if somebody wants to say, well, I am temperature, and here let us say you are measuring crystallinity, and you want to plot for, let us say, a triacetate. The crystallinity does not develop very easily, and then it develops. So, you can be sure, oh, crystallinity is developing, no problem. That means we can get setting by release of energy. But if you have this tenacity as another measure, so the tenacity goes and dips like this. So, when the crystallinity starts rising, the tenacity starts falling also badly. So, while it is thermoplastic material, it still cannot be very easy. So, what can we do to this? Well, if you really want a twist texturing, then you may have to get help by an external agent other than thermal, other than the heat that is the solvent. If you can do the same thing in the solvent thing, the solvent assisted texturing can be done at a much lower temperature, where solvent does exactly the same as the heat does. What does the heat do? Increase temperature, kinetic energy of the molecules increases, that energy becomes so high that the intermolecular bonds obviously break, and then the molecules are free to do what they want to do. In the case of solvent, the solvent diffuses inside the fiber, and then whatever little associations that they had, intermolecular associations, it breaks. When somebody said that nylon glass transition temperature goes down in water, so water is doing what? The nylon molecules form hydrogen bonds. Water, and these bonds are like contracts. Okay, it's not like an Indian wedding, for the whole, not life, this life, many lives. Okay. So, this is a contract. So, when the two atoms come close to each other, so they can exchange certain things, and therefore, they say, well, we are making a covalent bond or an ionic bond or a polar bond or a hydrogen bond, so distances, because they like that part. If hydroxyl groups here and hydroxyl groups from the other side come together, it's fine. Well, the water can also go and do the same thing. So, it can break that bond. Similarly, any other solvent will also go and break other bonds, and you have a new contract signed, and suddenly you will say, well, now the motion, molecular motion can take place at lower temperature, because solvent is assisting it. A lower temperature could be room temperature, it could be 70 degrees, based on what solvent, what fiber we are talking about. So, theoretically all fibers with the solvent assisted systems can work. So, but we are discussing what? Thermomechanical texturing. So, they are bad candidates for this. So, next in the material configuration, material parameters that could affect texturing, we said morphology, crystal morphology. Okay. So, one of them is called crystallinity. So, you understand crystallinity, how do you measure crystallinity? How does one measure crystallinity? X-ray diffraction. Very good. So, you can note this statement, and what is the statement says? During texturing, right, we are talking about thermomechanical texturing, partial melting and recrystallization of crystallites takes place to facilitate molecular rearrangement and stabilization. Recrystallization, see, partial melting and recrystallization. So, you must appreciate your material, which is called a textile material, to begin with is not amorphous. It has crystalline regions, it has also amorphous regions. And so, when we were talking about intermolecular bond breaking, so that molecules can take positions based on the best position, which means you have to handle the crystalline portions also, not just amorphous portions, which will respond easily. So, you have to go beyond that. So, there is always an energy barrier to be crossed, because it is already crystallized. We said, why it is crystallized? Because a fully drawn yarn. A fully drawn yarn had been stressed enough, so it can have stress induced crystallization. So, you have a crystalline material already, and then you have to partially melt. So, why do not you fully melt? Because if you fully melt, you will not have the fiber. So, you are partially melting and then doing enough, that means giving enough temperature, giving enough time for it to recrystallize, because sometimes smaller crystals can come together, make a larger crystal, all that is there. But what it therefore means is that it is not just the molecules in the amorphous region which are going to rearrange themselves, the material or the molecule within the crystalline regions also will have to be handled, which is thus must be happening. Then this also has something called a crystal structure. Some fibers are very good, like polyester. They have only one type of a crystal. Whenever they crystallize only in one form. But there are fibers like nylon, they have at least two forms. Then you have polypropylene, they may have at least 3 to 4 forms. That means it's a different crystal structure. So, when you say crystallize, then means it can crystallize into any form. So, that is the structure part of it. So, let us first look at the crystallinity itself. So, if it has certain amount of crystallinity and you want to go to a different thing, you have twisted the yarn and now you are heating it up and want a stable structure. So, what you have to do is you may have to, before any rearrangement take place, you may have to cross this barrier. There is an energy barrier, that is why you have to heat. If this barrier was not there, then automatically it would go to the lowest energy state. It cannot go because this may not be temporary set. We said temporary set also has a minima, but that requires very less energy to cross that barrier and go to wherever it wants to go. But in this case it is already a crystalline material. So, because there is crystallinity 20%, 30%, whatever, you have to overcome some of it. Only when you overcome this barrier, then the molecules will become free to go to a state which may be this state, where you will say I am now satisfied, right. So, if somebody asks a simple question, you have been given a choice, and what is the choice? That there are 5 materials with you or 3 materials with you, you can choose any one of them for texturizing. One of them has low crystallinity, other has high crystallinity. Which one will you choose? Low crystallinity. See, parent yarn, there is something called a parent, very important things. So, similarly, we have parent yarn. Parent yarn. So, parent yarn crystallinity should be low, is that right? Same question I repeat, I have texturized the yarn. So, I can measure the crystallinity of a parent yarn, take a call. After I have texturized, again I measure the crystallinity of the textured yarn, then I ask a question. Whatever process you have chosen, if the crystallinity of the textured yarn measured, one process has given you low crystallinity, other has given you high crystallinity, which one you prefer? In the case of parent yarn, we had to choose the parent yarn which had to be texturized. After texturization, the same question is being repeated. Now, I have a textured yarn, I have done some processing on it, I have measured crystallinity and I have got certain values. Which process would you approve? The one which gives you high crystallinity or the one where you have found crystallinity is low? High. Very good. So, what we have learnt here is that if choice is available, I will take a parent yarn with low crystallinity to texturize, but at the end of texturization I will like to have as high crystallinity as possible, that would mean more stable structure, alright. So, this is how we will do. So, we can stop here today and next I will pick up from here and move further. Thank you.